Changing from one basis to another is not too hard if one of those two bases is a natural basis of a vector space. We end up doing some more work, however, if we want to change bases between two bases that are not too natural. So let's look at the details. So first of all, changing basis from a non-natural basis to a natural basis is very easy. Let's call the non-natural basis C, and its elements W1 through Wn, to a natural basis. Let's call the natural basis B, with elements V1 through Vn. It's very easy. So if we have some vector little v in the vector space capital V, let's let v in brackets of B be the coordinate vector with respect to B, and v in brackets C be the coordinate vector with respect to C. So if we know the coordinate vector with respect to C, then we can compute the coordinate vector with respect to B by coordinate vector with respect to B equals P C left arrow B coordinate vector with respect to C, where this matrix P C left arrow B has first column coordinate vector of W1 with respect to B, etc., and then the last column is coordinate vector of Wn with respect to B. So in general, the jth column is coordinate vector of Wj with respect to B. So we do that for j equals 1 to n. Now changing basis from natural to non-natural is a little bit more work. So let's say from B to C is a little more work because we need to invert a matrix. In particular, we need to invert P C left arrow B. So in particular, we have, let's say, if we know the coordinate vector with respect to B, this is coordinate vector with respect to C. If we know the coordinate vector with respect to B, and we want the coordinate vector with respect to C, then we compute coordinate vector with respect to C equals P B left arrow C coordinate vector with respect to B. P change bases from B to C equals P change bases from C to B inverse. So we just need to invert this matrix, and then we can do matrix times vector multiplication, and we've got our answer. So the real trick is what if we have to change basis from one non-natural basis to another non-natural basis? So let's keep our natural basis B, our non-natural basis C, and let's introduce a second non-natural basis, C prime. And let's let its vectors be W prime 1 through W prime n. And square brackets V C prime is the coordinate vector of V with respect to C prime. Now theoretically we have so let's say we know the coordinate vector with respect to C prime, and we want the coordinate vector with respect to C. So theoretically, the coordinate vector with respect to C is a matrix times the coordinate vector with respect to C prime, and this is the change of basis matrix that turns C prime coordinates into C coordinates. But unfortunately, this matrix and its inverse are not so easy to find, at least not directly. So the matrices P C prime to C and P C to C prime are not so easy to find directly. And this is because the coordinate vector of W with respect to a non-natural basis is not so easy to see. The last formula we had involved a transition matrix, a change of basis matrix, whose columns were coordinate vectors of different vectors of a difficult basis with respect to a natural basis. But if neither one of these is natural, then this matrix and its inverse are simply just not going to be so easy to find directly. But the trick is, if we convert from C prime to B and then B to C, each one of those two conversions involves one natural basis. So let's suppose we know the coordinate vector with respect to C prime and we want the coordinate vector with respect to C. So we'll convert from C prime to B and then B to C. So each of these conversions involves one natural basis. So that means that one of the conversions is super easy, and the other conversion is sort of easy. It's an easy matrix, and then we have to invert it. In particular, we have coordinate vector with respect to C is, so we're starting with the coordinate vector with respect to C prime, and then we convert from C prime to B, and then we convert from B to C. Each one of these matrices we can find. So converting from C to B and then C prime to B and then B to C is the same as converting from C prime to C. And if you think about it, we can also look at this second product. If we have the coordinate vector with respect to C prime and we convert to B, then this is the coordinate vector of V with respect to B. So this product of matrix times vector is the coordinate vector of V with respect to B. And then we convert from B to C. So let's do an example. So let's let V be polynomials in X of degree less than or equal to 3. So the same example that we used last time. The natural basis for this space is 1x, x squared, x cubed, because every polynomial of degree at most 3 is a linear combination of these 4 powers of x. All right, now let's look at two non-natural bases. Let's let C be the basis we used last time. 1, and I guess I should have parentheses here instead of curly braces, really, because I mean let's remember the order here. So C is going to be the basis 1 plus x, 1 plus x squared, 1 plus x, I'm sorry, this one is 1 plus x squared. The last one is 1 plus x squared plus x cubed. And let's let C prime be the basis 1 plus x squared, x plus x cubed, 1 minus x squared, and x minus x cubed. Let's let p of x be the polynomial 2 times 1 plus x squared plus minus 1 times x plus x cubed plus 3 times 1 minus x squared minus 2 times x minus x cubed. So that is, it has the coordinate vector 2, minus 1, 3, minus 2 with respect to the basis c prime. So the coordinate vector of p of x with respect to c prime is 2, negative 1, 3, negative 2. So now let's ask, what is the coordinate vector of px with respect to c? And the solution is, first we'll convert the coordinate vector with respect to c prime to a coordinate vector with respect to b by multiplying by one matrix. And then we'll convert the coordinate vector with respect to b to a coordinate vector with respect to c by multiplying by another matrix. So it's p convert from b to c times p convert from c prime to b coordinate vector with respect to c prime. Of course, we're sort of thinking of this happening from right to left. We've got something with respect to c prime, we convert it to something with respect to b, and then we convert it again to something with respect to c. So the trick is to find these two matrices. So the coordinate vector, the change of basis matrix from c prime to b changing to the natural basis is always easy. All we have to do is copy the coordinate vectors of all the basis elements of c prime and their coordinates with respect to the natural basis. So c prime has coordinates 1, 0, 1, 0. The first element does. The next one has coordinates 0, 1, 0, 1. Because this is 0 plus 1x plus 0x squared plus 1x cubed. And then this coordinate vector is 1 plus 0x minus 1x squared plus 0x cubed. And then this coordinate vector is 0 plus 1x plus 0x squared minus 1x cubed. And then p b to c is the inverse of the matrix that we get by writing the coordinate vectors of the elements of c with respect to the natural basis. So we've got 1, 0, 0, 0, 1, 1, 0, 0, because this is 1 times 1 plus 1 times x plus 0x squared plus 0x cubed. And then 1 plus 1x plus 1x squared plus 0x cubed. So 1, 1, 1, 0. And then 1, 1, 1, 1. And this is a matrix that we inverted last time. And we found that its inverse has rows which are 1, negative 1, 0, 0. 0, 1, negative 1, 0, 0, 0, 1, negative 1, and then 0, 0, 0, 1. I see I'm running off the screen here. So 1, negative 1, 0, 0, 0, 1, negative 1, 0, 0, 1, negative 1, 0, 0, 0, 1. So that's P converting from B to C. And we want to take the product of those two matrices. So that means that the coordinate vector of P of x with respect to C is, so we've got the B to C matrix, which is right here. So 1, -1, 0, 0, 0, 1, -1, 0, 0, 0, 1, -1, 0, 0, 0, 1 times the C prime to B matrix, which is right here. It's almost a checkerboard of ones and zeros, except that these last two ones in the lower 2 by 2 matrix are negative. All of that times the coordinate vector with respect to C prime, which is 2, -1, 3, -2. All right, when we multiply these matrices together, first row is going to be first row minus second row. So that's 1 minus 0, 0 minus 1, 1 minus 0, 0 minus 1. Second row is going to be second row minus third row. So that's 0 minus 1, 1 minus 0, 0 minus -1, 1 minus 0. The third row is going to be third row minus fourth. So 1 minus 0, 0 minus 1, -1 minus 0, 0 minus -1. And then the fourth row is just going to be the old fourth row. 0, 1, 0, -1. All of that times 2, -1, 3, -2. And we get 2 plus 1, which is 3, plus 3 is 6, minus 2, plus 2 is 8. Then -2 minus 1 is -3, plus 3 is 0, minus 2. Then 2 plus 1 is 3, minus 3 is 0, minus 2. And 0 minus 1 plus 2. Minus 1 plus 2 is plus 1. So there's the coordinate vector of our polynomial with respect to the basis C. The end.